Hello and welcome to Dare to Know, interviews with quality and reliability thought leaders. I'm Tim Rogers, and today I'm pleased to welcome Shane Turcott. Shane Turcott is a metallurgical engineer and a Canadian professional engineer specializing in laboratory-based failure analysis. His work provides physical evidence and support to reliability engineers conducting RCA investigations throughout the refining, mining, and energy industries. He's worked for various companies, including Dofasco, Bodycoat, and Liberty Turbine Services. In 2009, Shane founded Steel Image, an engineering company specializing in failure analysis and on-site material evaluation supporting reliability. He's the past Ontario chair of the American Society of Materials and current architect for the ASM World Class online series at asmontario.org. That's O-R-G. Shane is also the author of Decoding Mechanical Failures, the definitive guide to interpreting fractures, which is pretty likely the first introductory book explaining how to examine fracture surfaces. Shane Turcott, welcome and thanks for joining us.
Tim, it's really great to be here. I'm really excited.
Well, we're excited to have you as well. Shane, your book, Decoding Mechanical Failure, is really a great contribution to the practice of mechanical failure analysis, in part because you've included so many photos and diagrams showing the physical evidence of failures. You know, I know this is an audio podcast, but can you describe some of the examples from the book?
Sure, Tim. So, I mean, first of all, I want to say thank you. That was a really nice thing to say about the book. So a lot of people, when they first get the book, the first thing they say is that the quality and quantity of the pictures is really impressive. And I think that's one of the things that makes this book unique. There is a lot of books out there about failure analysis, and they do include pictures. But when I started this project, it was clear to me if this was going to be the very first book on how to examine fracture features and fracture surfaces, it just had to be filled with copious amounts of large, high caliber color photographs. Because I think that is really the only way to learn how to examine fracture surfaces. Now, for examples, I've done my very best to put a wide range of samples in there. Everything from gears, shafts, bolts, chain links. There's a crane hook in there. I've tried to choose components that were simple to understand how they're used, that are very common in industry, and create a really good place where to begin learning how to examine fractures. Now, to be a bit more specific about some of the examples, because I think that's what you're asking me to do, describe some of the examples. One of the sections I'm really proud of is a section on fastener failures, on bolts. Did you know, Tim, that you could look at a bolt fracture and be able to tell very quickly whether or not it failed because it wasn't installed correctly, it didn't maintain its preload, or if it failed because of excessive loading or it was overloaded?
Well, I might have guessed, but I certainly haven't seen the physical evidence of all three of those situations. So I probably would have had to guess. You know.
That's what I'm trying to create a tool that people don't have to guess. They could technically pick it off the ground, look at it, and already have some good ideas as to what caused it to fail. And that's, I think, one of the sections I think is going to, 10 years from now, people are going to look back and actually it'll be a lot easier for people to do bolt failures and fastener failures.
So let's just talk about bolt failures let's focus in on that a little bit, Shane, for a minute. How exactly does the physical evidence from a failed part suggest different kinds of failures for a bolt?
Okay, so to answer that question, let me take a step back. So first of all, diagnosis is the first step of solving any problem. Okay, so like a doctor the first thing a doctor has to do when they have a patient is make sure that they properly diagnose what's wrong with the patient before they can treat it. And for a doctor, that'll always start off with a visual triage of the patient, and they may choose at some point to do additional testing. But before they get to that point, they're going to ask lots of questions. That's your background data. And they're going to basically examine the patient to find out as much information as they can. Well, equipment failures are the same. You have to be able to diagnose to be able to understand why it failed. And that initial triage is incredibly important to figuring out where the direction of your investigation is going to go. Now, when a part fails, the failed part itself is the largest source of information. And so physical evidence is needed to understand why it failed. And that triage is really important that is done and done well. Now, each fracture when it forms, each different type of mechanical failure mode, they form very distinctive features, whether it's ductile, brittle, or fatigue. And it doesn't take that much training to start picking out information from it that explain things such as the motor, like the loading that caused it to fail. Is it a single impact? Is it a slow pull apart? Is it thousands of loading cycles, or is it millions of loadings of cycles? Information such as where the crack starts from. Does it start at a sharp corner, uh, at a weld, at a material flaw, the area that you think would be highly loaded or area that isn't? And you can also start picking up things from the fracture surface that might give you indications if there's quality issues with the part itself. If the material is not as strong as it should be, if it's not been made correctly, there are some things with a little bit of training you can start picking these out.
Are people getting this kind of training? I mean, it seems like this seems so fundamental and so basic. Are people not getting this kind of training?
So I don't think that this training exists.
Wow.
So there are many industries that overlap as far as the interest of this. There's inspection. People who spend their entire career looking for cracks. It would be great if they could have a bit of training how to interpret that cracks. There
No
are
kidding.
reliability mechanical engineers who are dealing with, in the design phase or out in the service that parts fail. And then there's my own industry, a metallurgical engineering. Um, how I learned was through apprentice style because there was no books on introduction to what we call fractography, the science of looking at fracture surfaces.
Right. So again, I guess I'm kind of, I know this is we're doing a podcast here, and your book has so many photographs, but can you just kind of describe what different kinds of different kinds of observations that lead to specific kinds of failures? Can we just use a bolt for an example?
Okay, so before we talk about a bolt, if we're going to talk about fatigue, which is one of the most common ways a bolt can fail,
Sure.
you first of all have to be introduced to fatigue. Okay, so there's a few features that define it. Actually, there's five visual features. First of all, fatigue will have three zones. There'll be a place obviously the crack starts from. It'll grow through and then it'll change. That change is called the final failure zone, the final place to fail. You
Right.
could have what's called crack arrest marks, sometimes called beach marks, that give you indications it's progressive crack growth. You could have features such as ratchet marks that tell you that multiple cracks first started. Um, and all these become very useful once you start recognizing what they are. You could actually use them for different things. Now, bringing it back to the bolts, once you have an idea of the size of loading, so that final failure zone, the final area to fail, if you can size that up relative to the bolt, you're going to get an idea of whether the loading was very low for that strength of bolt, which means that had it been installed properly or maintained its preload, wouldn't have failed, or whether the loading on the bolt was excessive, which means either the loading was far more than the bolt was designed to withstand, or you've used the wrong bolt or the bolt's weaker than it should be. So perhaps a long answer, but there's a lot once with a little bit of training that you can start picking out that can tell you a lot of what happened to that bolt.
You know, we rely a lot on in reliability. We rely a lot on testing, and we a lot of our listeners have used performance data or test data to support their root cause analysis. Um, again, it just seems so fundamental to me that you'd want to inspect the failed part. You think there might be situations where the data points in one direction, but the physical evidence points in a different direction as far as root cause is concerned? I mean, could people be making mistakes about root cause because they're neglecting the physical evidence?
Okay. So first off, I have to be careful. I am a metallurgical engineer and I support a lot of reliability professionals, but I'm not a reliability engineer. Um, and so I want to say that first of all, is that what reliability engineers are doing is working. That I mean, the efforts and practices they're using, if that's using performance data or test data, they're doing a great job reducing it. But I still think we're leaving something on the table when we're not looking properly at the failed part itself. Um,
Sure.
And maybe a really morbid example, hopefully this doesn't throw anyone off here, is if you were doing a murder investigation and you were to say to the investigators, you can look everywhere but at the body. You can get all the data you want from the room. You can do all this kind of stuff. Um, you might get a lot of things that might point you in the right direction to who the culprit was and how the murder happened. But there's no greater source than the actual body itself. Now, I'm not proposing that we train that lead investigator to do all the forensics they would do in a lab, but for sure, with proper training, they can get a lot of information from it that when they connect with the physical evidence around it. Um, and so that's, I guess, the best analogy for this as well. I think that there should be a triage that reliability engineers can do and such. Now, going back, one of the questions you asked was, could people be making mistakes? And the answer is, and I think it's the elephant in the room. The answer is yes, it does happen. Okay, and not at a high rate, but it is happening, and we know that because there's facilities that have repeat failures, that people have tried 1, 2, 3 times to do RCAs, and haven't been successful at catching and preventing that failure. And I mean, I don't envy people who are working with data sets that could be incomplete, data sets that might be overwhelming. You don't know if you have all the variables captured that it could be. There's probably times where the data is not clear, or that there's no culprit, or that there's three culprits. You have to figure out which one it could be. Um, and so what I'm saying is that we can reduce some of the guesswork if we combine the performance data with that initial assessment. And I think a really good term that I always find of interest is that, like, when all you have is a hammer, all you see are nails.
Right.
And my answer is, why don't we add another tool to the toolbox?
Yeah, like I say, it just seems so obvious to me. Using the failed part as a real indicator. Uh, can you think of any reason why this isn't happening? I mean, what are some of the reasons why people aren't making a broader use or wider use of this as a to provide insight into what's happening?
Okay, so first of all, I mean, when it comes to the use of physical evidence, there are a lot of people who are using it, and I think there's a lot of people who are talking about it. Um, but those people are usually third-party off-site laboratories that are doing it, and that's what I do at Seal Image. Is that when a reliability engineer has a failure, they can send it to us, and for all the listeners, we're happy to do it. We'll give you the most amount of information we possibly can with every tool in our laboratory to help solve the problem. But the problem is that we know that there are a lot of RCAs and a lot of reliability engineers who are doing projects that they can't bring in laboratory services, or they're choosing not to. And I don't think this has to be an all or nothing. Yes, a lab will always provide more information than just the triage. But if it's going to be an in-house investigation, I still think that anyone leading that investigation or a part of it should just have the basics to being able to examine the failed part and get a lot of information from it, and then decide how best to go next. Um, and I also want to say too, like, this isn't, not only does this increase the confidence of the investigation, it actually might reduce a lot of the work. One of the sections in the book has a chapter on shafts. Um, and once you get familiar with fatigue, you can go even further and look at shafts and get familiar with fatigue for shafts, and say within 1 minute of seeing a fatigue failure of a shaft, whether the problem was that caused it to fail, whether the problem was a stationary component, like say misaligned bearings, bearing damage, or a rub situation, or on the other side, if the problem was amongst a rotating assembly, if you've got a bent shaft or a misaligned coupling, very quickly you can know whether it's you have to go left and you don't have to investigate right, or whether you should go right and you don't have to investigate left, reducing the amount of work you have to do.
Shane, we've been focusing on physical observation, just inspection of the failed part. Um, are there other ways of inspecting, other ways of looking at a failed part, other inspection techniques besides just visual inspection? Are there other non-destructive techniques that you recommend?
I think every one of those would be customized to the problem. Um,
Got it.
there are a lot of really good inspectors out there. I think making sure you properly survey the damage is really important to know if you've got, if you have one crack here, you got to know if it's systematic, you have many cracks other places. But that would be customized very much so. And I would hate to convince anyone in this audience that I'm an expert of that.
Okay, that's fair. I keep coming back to this question of why we don't see more inspection of failed parts. I wonder if in a lot of cases whether the parts are even available for physical inspection. I'm sure there's situations where the part is just discarded. And it's not available, or it's because there's such a strong desire to get things back up and running quickly. So if there's a failed part, let's replace that failed part with a good part, get everything up and running again, and the part that failed may get thrown away.
Yeah.
Maybe that's part of what's going on.
So that is definitely something that happens. But I also think that shows that people don't value the physical evidence, that they don't
Yeah.
value that initial triage. If everyone's, if no one has instructions, save the part, and that's just not a habit, that is a sign that it's not being done right now. And
Oh,
and
I agree.
and a little bit off topic, that is, I think that once people start using and start learning the basics of how to examine fractures, and a rotating engineer can then go up and walk up and be like, there's a problem amongst the rotating assembly because I have looked at the fracture surface. I think there's going to come a time in the future that people will come back and say, when they're discussing RCAs of the past, is why didn't we include looking at that fracture surface? Because it actually is quite obvious. It just should be done.
Shane, this is kind of a leading question, but what's the best way for reliability engineers to work with specialists like yourself, like metallurgists? What kind of recommendation would you make in order to build a better partnership between these two groups?
So first of all, I always say is find a metallurgist or a failure analyst, mechanical engineer, metallurgical engineer that you trust. Okay, because I think you're going to be working with that company or that person for a very long time. But it's about discussion. You know what I mean? I've worked at a lot of labs where there's not a lot of communication back and forth. We're doing parts, we don't know what the history of the part was, if it was the first or the third failure to occur. It would just be communicate as much as possible. You want to provide material type, you want to provide discussion of how the part was used, any recent changes you made to your operation or that assembly itself. Um, and then I'd also suggest too, if the results you get back don't match, have that conversation and continue to push and work back and forth and build off each other until you get an answer that makes sense and matches with the perspective you guys see.
That makes sense. Shane, listen, this has been really great. Thanks so much for being with us today.
This has been a lot of fun. Thank you for having me.
That was Shane Turcott, principal metallurgist at Steel Image and author of Decoding Mechanical Failures. To learn more about Shane's work at Steel Image, please visit Steel Image, that's all one word, steelimage.com. This is Tim Rogers. Thanks very much for joining us.